Right now we're going to look at a little bit more complicated problem. That's Kepler's third law, which describes the period of the orbit of an object and its relation to the size of the orbit, so-called semi-major axis. Here we're talking about planets orbiting the sun, but the same rule applies to a moon orbiting a planet. So let's just concentrate on the planetary case. Kepler developed this law by looking at the data collected by Tycho Brahe. Kepler did not have a theory for explaining why this should be the case, and that had to wait until Newton came along over 100 years later and used his law of gravitation to show that Kepler's law is indeed what one should expect. And using Newton's technique, you can calculate this relationship. It's pretty elaborate, takes pages and pages and so forth. Here we're going to do it in a rather simple way. So here's the analysis. And we're in the process of doing Kepler's third law. We are going to develop a generalized technique for doing this kind of problem that I'm going to illustrate now. So we want to compute the period of the orbit of a planet in relation to the key parameters that we can identify, and here they are. So we want the period of the orbit and what would dictate that period. So we've already said that the size of the orbit, the acceleration of gravity at the location of the orbit, which we'll call g, and the mass of the planet, m. Those are the only three things we can identify that might be involved. So the idea is to write down a sort of a dummy equation. The period of the orbit on the left, and then some combination of the gravity raised to the a power, the size of the orbit raised to the b power, and the mass of the planet raised to the c power. We don't know a, b, or c, but we're going to derive them using dimensional analysis. So rewriting this equation in terms of the units that are involved, the left side just has time, so there's the time. Acceleration is length over time squared raised to the a power. There's that little a again. Here's the size of the orbit, which has the units of length raised to the b power. That's this b. And the mass of the planet raised to the c power. That's the units of mass raised to the c power. And there are really three equations here, which you're going to write over here. So let's look at the length equation first. On the left side, there's no units of length. On the right side, length appears in two places. So we have an a and a b. So these powers are what we're going to work with. So a plus b here has to equal 0 because there's no length on this side. And there's this equation, a plus b equals 0. Let's look at the mass equation. There's no mass on the left side, so we're going to have a 0. And the only place we find mass here is raised to the c power, which says that c equals 0. Right there, there's the mass equation. And the time, this one is raised to the 1 power. And time appears over here, but it appears in the denominator here, squared and raised to the a power. So we're going to have a 1 equal to minus 2a, because this is in the denominator. And there it is, minus 2a equals 1. And we can solve this little set of equations. We can see that a is equal to minus b, c is equal to 0. This one right away tells us that a is equal to minus 1/2. So there's a equals minus 1/2, and a and b have the same value but opposite sign, so b equals plus 1/2. C equals 0. So we find that the period of the orbit, you place these a and b and c values here in our original equation, the mass goes away. M to the 0 is just 1. So we find that the period is equal to this square root of the size of the orbit over the acceleration. Unfortunately, maybe I can fix that right now. That this should say that should be a G. I'm going to fix that right now. Let's see if I managed to do that. Yes. Okay. So sorry for that little editorial diversion. The period looks like this, the square root of L over G. Remember, we got the 2 1/2 from our set of equations. Size of the orbit divided by the acceleration of gravity at the location of the planet. And we probably are missing the 2 pi. Remember when we did the pendulum thing, we missed the 2 pi. So this is the scaling law. The actual value of the period equals 2 pi times this. That's why we changed this symbol, which means proportional, to this sign that means equal. Now, right now we don't know what G is, the acceleration of but we can figure it out. So Newton said force of gravity is his constant times the mass of the sun, and here we can use Earth as the example, mass of Earth over the distance squared, and we want to figure out what G is. So Newton has his law of gravitation. He also has his force law, so that's what these are. Force equals mass times acceleration, and the ME's cancel, and so we get this. The acceleration at the location of the planet is G, M of the central body, over the distance squared. And if we put that into what we got from the prior page, namely this, we get this, that the period should be 2 pi times the square root of the cube of the size of the orbit. And that's exactly what Kepler said, that the period is proportional to the square root of the cube of the size of the orbit. And our dimensional analysis gave us this business. Kepler didn't know about this, that G times the mass of the sun is the proportionality. Now, we can do, later on, if you follow this in more detail, you find that there's a small correction because the presence of our planet changes the position of the central body. So the actual final result is this. But we see the power of dimensional analysis. It gave us this result. We didn't have to do any elaborate physics. We did have to know Newton's law of gravity, but you probably wouldn't be doing this kind of problem unless you were familiar with this. All right, so in any case, here's Kepler's third law. The ratio of the periods of 2 planets goes as the cubes, the square root of the ratio of the cubes. Because if you do this ratio, the 2 pi, the G, and the mass all disappear. So we have Kepler's result, a fairly efficient way to calculate that. We can go on to look at another of Kepler's laws, which is that the rate at which area is swept out by, here's the sun, for example, here's a planet. The rate at which this area is swept out is defined by this equation. Kepler found that. From this, we can see if we can understand how to calculate the speed, the velocity of the planet. Because what Kepler said was the areas swept out in an interval of time are the same no matter where the planet is in its orbit, even if it's an elliptical orbit. So let's do dimensional analysis on speed of a planet. And we're going to use the product of G times the mass of the sun as a key parameter, and the size of the orbit as another parameter, and that's just pretty much it. This choice to do this comes from this kind of thing. That we see the period depends on the cube of the orbit, the square root of the cube of the orbit, divided by this product, and this product is a constant, right? It's the Newton's gravitational constant times the mass of the sun. So we'll use that here. raise that to the a power, and the size of the orbit to the b power. All these things have units, which we'll look at in a second. Speed has the units of distance over time. There it is. Gravitational constant times mass. If you go look up the units of Newton's gravitational constant, you'll find that it has mass in the denominator. So this product has the units of L cubed over T squared. We raise it to the a power. The distance has units of length raised to the b power. So we have a L to the 1 here, and on the right side we have L cubed raised to the a power, that's 3a, and then we have a b. So we have on the left 1 equals 3a plus b. On the left for time is in the denominator, so we get a minus 1 here for the power, and here we got minus 2a. So we have these two equations. And we have two unknowns. And if we solve this simple, you can see right away from this that a is equal to a half. And a is the power of the product gm. So we get a square root of gm. And then if you use that value of a here, you get b here. And so the speed looks like this. And once again, we can calculate Kepler's law that the area swept out is the same for any interval of time, regardless of where the planet is in its orbit. So the area swept out forms this kind of triangle. So it's the speed times the distance this distance from the sun, divided by 2, because it's a triangle. This area has always, the area is divided by 2. And we have the speed right here. So we have L over 2 times the speed, which we already calculated. We do some arithmetic and we get this result. And we notice something, that the area swept out in a unit time is a constant, because G, M, L, and 2 are all constants. Okay. Now we're going to do wave speed. So ocean waves, and see a little typo to take care of here, so you can see the reference for this. And